Hello, my name is Han Kun Lee. I am a PhD candidate in the Electrical and Computing Engineering Department at the University of Illinois at Urbana-Champaign. I'm being advised by Professor Cunningham and being co-advised by Professor Mindo. The title of my presentation is Single Molecule Localization Microscopy, SMLM, from Fundamental to the Deep Learning. Single molecule localization microscopy is a family of powerful imaging techniques that dramatically improve spatial resolution of standard diffraction limited microscopy techniques. And it can also image biological structures at its molecular scale. And for those who are not familiar with what diffraction limit is, I am going to cover what those are. But for instance, for diffraction limit images are what was shown on the left-hand side, where it's the sample that we're trying to image shows very blurry images, while the single molecule localization microscope images can actually show a very clear images of the diffraction limited images. Before I get into the detail, I want to make sure that I want to give credit to Professor Jeff Lichman, who provided this wonderful lectures, which covers most of the fundamentals of the diffraction limits. For those who want to take a look at his lecture, please use this link to watch his lecture. But back in the days, people thought that the lights are acting more like a straight line, and the ray optics models light as a collection of rays traveling in a straight line. Example of this ray optics is a pinhole camera, where a pinhole or tiny hole is in the center of the camera. When light hits an object, it scatters everywhere, but only a certain portion of the light will pass through this pinhole and will reach the imaging plane. Same thing as here in the bottom of the lamp, the light will scatter everywhere and only a portion of the light will pass through this pinhole and form an image at the imaging plane. And because it's a straight line, it creates an inverted image. What would happen if you increase this pinhole size? Instead of the image being more clear, now it becomes more blurry. It is because more portion of the light is passing through this pinhole and therefore forming an image at different locations, and therefore the image becomes more blurrier. So can we reduce this pinhole size to infinitely small and then make a crisp image? However, if in this case, it's actually not. And in order to understand why this happened, we need to understand what the wave optics are. The wave optics models light as electromagnetic waves. So before I get into the details of the wave optics, we first need to understand some of the terminologies. The wavefront is a surface of a wave where all points are in the same phase of their vibrations. So what it means is that we have a sinusoidal wave that are traveling in this one directions, and when its highest peak is what we call the crest, and when it's at its lowest peak is what we call trout. And you can think of this as like this, where we have a wave that are traveling in one direction that are in the same phase, and therefore we have all crests or the peak lined up and form a wave front. And wave fronts are where the crest is at. And when they are in parallel to each other, traveling in the same direction, we see a plane wave. And when these waves are diverging from each other or converging, they are called the spherical waves. And this wave optics is actually originated from a Dutch mathematician. His name is Christian Huygens. And wave optics was his big idea. And Huygens postulated that the light at its most elemental is a distribution that propagates in all directions as a spherical wave. He called these elements of light wavelets. And wavelets can be thought of as an elemental unit of plane or spherical wave. Instead of a plane wave, this plane wave consists of many different wavelets. They are emitting lights in all directions. And you can think of it this way, where all these wavelets, when they interfere with each other, they create a constructive interface, and therefore this is where the plane wave, the crest is at. And when these points are converging when these are points are in a kind of a curvature, they point to one direction, and this is what we call the converging spherical wave, and this is diverging spherical wave. Explanatory power of wavelets is evident in the phenomenon called diffraction. Imagine that you have a single point source in a box, and we also have a slit in one side of the box. If the light is just a straight line, then we'll only see a very tiny straight line coming out. However, we see the light that are spreading all different directions, and this is because of the diffraction. We only consider one slit, but in this example, we're going to consider two different slits. We see that the waves are coming from a point source, and this wave is consists of wavelets. And on this top slit, only single wavelet passes through. And because this wavelet is the elementary unit and it propagates, it emits light in all directions, we can see that it creating this kind of a pattern or circular pattern traveling outside. Same thing goes here, where we see a single wavelet passes through and it will create this circular pattern over the space. However, when they are interacting with each other, this interference patterns form. And when these two waves are coming together in same phase, this is what we call the constructive interference. And this when two waves are canceling with each other, this is what we call the destructive interference. And this is why we see some fringes where we see bright area, dark area, bright area, and dark area, and so on. So let's look at how the microscope lens system works. We have a point source, and then it will actually create a spherical wave, and it is collected by the objective lens, which makes this spherical wave into a plane wave. This plane wave is now goes through the tube lens, which focus the plane wave into a point source, and this is where the light is converging into a spherical wave. The question is now then, for a point object on a focal plane, such as infinitesimally small fluorescent bead, what is the distribution of light at and near the image plane? And this is what we call the point share function. And what is the point share function of this infinitesimally small fluorescent bead when the light passes through the microscope lenses? Just like before, we're going to take a close look at this area where the lights are becoming to converge. Each of the infinite points in the emerging wavefront, which is this, acts like a point source. Each point emits a wavelet, which are the elementary unit of this wave. All wavelets from the same wavefront are mutually coherent, that is, they all oscillate in synchrony. Therefore, they interfere with each other in a predictable way. So instead of taking a look at all different wavelets at the same time, let's simplify the problem and let's only look at the wavelet that are far from each other, the edges one. So it's like from the previous example, because the wavelets that will interfere with each other depending on where the locations are, they're going to create constructive interference, destructive interference, and constructive interference, and so on. So this is what we see on the space where we have two different wavelets that are interfering with each other. At an instance in time, which is shown on the right top side, the mesh of dark and bright lines are showing what we're seeing is intensity of this pattern, including the RI or the CMOS or CCD camera. This intensity is proportional to the amplitude square. So just like before, this detected interference pattern has dark, which is the destructive interference, and bright lines, which is the constructive interference. So far, I only talked about the pattern that two different wavelengths are creating. I did not even talk about the question that we were first asked. What is the pointer function when the light passes through the objective lenses for the microscope system? In order to answer that question, we first need to understand the objective lens first. The objective lens vary in their numerical apertures. Some have low numerical aperture, some have medium numerical aperture, some have high numerical aperture. Most people think that objective lens only concerns about the magnifications of the images. However, what the most important aspect of the objective lens is that it determines the resolving power of the microscope. For instance, in a low numerical aperture objective lens, the light that are being collected by the objective lens, you can see that there are smaller cone of light is being collected, and as it gets higher numerical aperture, we can see that more cone of light is being collected by the lens. It is, even though it is also true that magnification is related to the focal length of tube lens divided by the focal length of the objective lens. However, the objective lens, depending on the objective lens numerical aperture, we can achieve a better resolution. So for a high numerical aperture objective lens, we can see that more light is being collected, and therefore we can have a bigger plane wave that can propagate and more spherical wave farther apart from each other. While for the low numerical aperture objective lens, smaller plane is created and smaller spherical waves closer together. What it means is that the extreme points of these waves are farther apart from each other, while the low numerical aperture one extreme points are more closer to each other. So from previous example, we saw the effect of these two different points, wavelets, and how they create fringes or the patterns. And when these two wavelets are far apart from each other, in the case of high numerical aperture, we can start seeing that it gives short fringe periods and gives narrow fringes. And when these wavelets are closer together, you can see long fringe periods and wide fringes. Up until now, we've only considered two wavelets. However, what if you consider three different wavelets? We can add them together and we now see different pattern. And this is where the focal plane is, where this center line is equidistant from each wavelet point. And then if you start adding more wavelets, we can see now that the light is being collected at the center of the image plane even more. And then when we add infinite number of wavelets, now we clearly see that all lights are being focused on the center of the image plane. So all wavelets in phase are at the center of the image plane. Light is concentrated in the middle of the image plane. Other fringes or side lobes progressively get dimmer than the main peak. Most of the light is within the cone. Width of the main peak, which is here, is set by the extreme pair of the wavelets at the rim of the lens, hence by the numerical aperture. Just like here, if the wavelets are far apart, it creates short fringes patterns, and therefore it can actually create very, very tiny peak width. However, if these wavelets are far apart from each other, they will create even wider peak width. So the effect of numerical aperture on pointer function is that if we can collect more light, if the wavelets, the extreme points are far apart from each other, it creates wide separation between wavelets possible, and as a result, small central peak. However, if we use low numerical aperture, the central peak gets broader. And this can also be explained using the Fourier optics. The Fourier optics says that if you have a positive lens, and if we're trying to image an object in a object plane, and when it goes through this positive lens and at the end of its focal point, this is where the Fourier plane is. So the lens will actually perform Fourier transform for us. So what we're seeing in this plane is a Fourier transform of the object that we're trying to image. For those who have previous knowledge of Fourier transform, would probably recognize this right away. If we have a sinusoidal frequency image, and if you take a Fourier transform of that, we'll see dots that are kind of close together, while if we have high frequency component in our image, we see dots that are kind of separated apart from the center. This means that at the center of the Fourier plane, this is where the low frequency components are, and as it gets away from the center, the higher frequency components are represented. And the higher frequency component tends to travel upward, and therefore it is not collected by the lens. And this is why it is very critical to have an objective lens that can collect more lights that are kind of diverging from the center so that high frequency component can be contained throughout the imaging. The maximum spatial frequency is also determined by the wavelength itself. And the frequency, spatial frequency, can only be less than 1 over the wavelengths, and this is why the light microscope can only be as good as the light source. So back to the question of the Poincare function. What is the distribution of the lights when we're trying to image an infinitesimally small fluorescent bead, and the lights are collected by the objective system? And this is what we show. Instead of showing a very tiny spot, just like an infinitesimally small fluorescent bead, we're now seeing a little bit bigger circle that is not even close to being a very infinitesimally small spot. And if we actually increase the contrast, we're seeing this kind of a ring pattern. And this is what we call the area disk. The Poincare function has center, area disk. Poincare function has a series of concentric rings. The larger rings have progressively lower intensities, and the first dark ring radius can be calculated using this equation, 0.61 lambda over NA. And this, in fact, is turned out to be the resolution that we're looking for. And in the actual direction, so we have z-axis this way, we have x-axis this way, the optical direction. Turns out that there is more spread along the optical directions, and first dark isolation at 2n lambda over NA squared. So the second question now is how close can two equal point source be and still be seen as 2 points? And this is directly related to the Rayleigh criterion. You can see that on left-hand side, top left-hand side, we see that these are 2 different light source points. However, when it gets closer and closer together, we now see that nobody would disagree that this is a single point source. So what is the distance that these 2 point sources can be close to each other and still be seen as 2 different points? And that is a Rayleigh criterion. And the Rayleigh criterion states that when the first light source, the lowest point, darkest point, is at the center of the neighboring Poincare function's peak. So this is what we call the resolution limit, and this is what we call the Rayleigh criterion. Same thing for the axial direction. It is a little bit bigger, and it's the distance is a little bit bigger than the lateral direction. If you use low numerical aperture one, we can see that this is just a blurry image, and nobody will be able to tell how many source molecules are in this image. However, if you start using the higher numerical aperture one, it's very clear that how many points are there. You can also see the rings pattern as well. And in a low numerical aperture, if you take a Fourier transform, then we see that the higher components, higher frequency, spatial frequency components are not visible. However, in the higher numerical aperture one, you can also see the higher frequency components visible in Fourier plane. The resolution, Rayleigh criterion, or the diffraction limit resolution, is not the only one that determines the resolution when it comes down to imaging, where it involves camera to image what we're seeing. And in order to understand that limit, we first need to understand the Nyquist limit. The Nyquist law, named in 1933 after scientist Henry Nyquist, states that a sound must be sampled at least twice its highest frequency in order to extract all the information from the bandwidth and accurately represent original energy. So what it actually means is that if we have a signal that is like this, then we must have a frequency twice the frequency of this frequency to extract all the information, including the highest frequency component, as well as the lowest frequency component. So in this case, if the ratio between sampling frequency over the highest component frequency of the information is more than 2, then we can accurately extract all the information. However, when it goes down to even sampling frequency is even lower than the twice, then we start losing this information, and therefore it is critical to have this ratio above 2. So the resolving power can also depend on the camera itself. We learned that the resolution limit is set by the Rayleigh criterion, which is 0.61 lambda over NA. However, the McPherson limit also specified that it has to have twice the frequency. So the ideal pixel size is the half of this, which is 0.3 lambda over NA. If you don't have that, we're going to, even though we can technically differentiate these two different point sources together, what we're going to see in the image is just one single point source. But if we need more resolution, what then? We can start using a higher numerical aperture or a higher index immersion liquid, or we can start using shorter wavelengths. Good example of using shorter wavelengths is the scanning electron microscope, SEM. SEM utilizes the electron as the light source, as the source to resolve the image, and the wavelengths can be calculated by de Broglie wavelengths, where wavelengths is Planck's constant over the momentum. If you increase the momentum to about 100 kilovolt, the wavelengths can even go down to 0.0037 nanometer. However, the SEM requires a lot of preparation. We gotta scan, we gotta coat the surface, we gotta prepare the sample, and then put it into a vacuum, and imaging takes about more than an hour. And so it is a very complicated process where if you were to image the live cell, it will not be possible. So can we achieve lower resolution without using SEM? And yes, and that is using the single molecule localization microscopy. The concept of single molecule localization microscopy was originated back in 1995. However, it was not possible to realize this concept due to the difficulties in technological difficulties. But nowadays, due to the advancement of the semiconductor technologies, it became possible. And single molecule localization microscopy is fundamentally based on the fact that the spatial coordinates of single fluorescent molecules can be determined with high precision if their point-to-a function do not overlap. What it means is that if we have a sample that looks like this, and somehow if we can activate a subset of this molecule so that only a subset of them generate fluorescent light, we can image them and then perform a point spread function analysis to find the centroid of this point spread function and deactivate this fluorescent light, and then activate another subset of fluorescent molecule that are spaced apart, and then repeat this many times and collect all these different centroid points to create a super resolution image. Just like before, we have diffraction limit images. Now we can stochastically or randomly activate a subset of molecules that are farther apart from each other, and we can image them over time, and we can localize the centroid of each pointer function and combine them to create a super resolution image. How we can achieve that is because due to a stochastic blinking of fluorophore, and this fluorophore normally fluorescent by going from the first excited single state to the ground state. When they're shined with excitation light, the electrons will actually move from ground state to the excited state, and then when they fall from excited state to the ground state, they generate fluorescent that have lower energy and therefore longer wavelength. But sometimes instead of going back to the ground state, the molecule undergoes intersystem crossing into a triplet state or the dark state. And in this triplet state, it's forbidden to relax radiatively so that the molecule stays in the dark for microseconds to milliseconds. While it is in triplet state, it cannot emit photons, thus off time in the blinking pattern. And when it finally comes back, because they are in a low energy state, their emits they come back in a different form, either through heat vibrations, or it can actually emit light that are kind of longer wavelength that are not visible to us. Using this phenomenon, there are two major ones. One is the photoactivable localization microscopy, which what we call the POM, and also stochastical optical reconstructor microscopy, what we call the STORM. The concept is the same. They use stochastically or fluorescent molecules that are spread apart, and then use the localization method to create the super resolution image. However, they use different fluorescent molecule to achieve this. I'm not going to talk about both of them, but I want to talk about the storm in the rest of the lecture. First, the first storm paper came out in 2006, and they have demonstrated that they can even resolve between 26 nanometer difference. And also they have shown that they were able to resolve this circular DNA and also show that they can resolve this. The way that they actually did it is that they applied this algorithm where they assume that the area pointer function is, it follows the ellipsoidal Gaussians, and this is the Gaussian equations where A is the background fluorescent level, I naught is the amplitude of the peak of the Gaussian, A and B defines the width of the Gaussian along the x and y directions. X naught, y naught describe the centroid, center coordinate of the peak, which is here. And this is just a transformation matrix to account that the Gaussian is not always in a single direction, but rather it can actually rotate in all different directions. And therefore, the data is a tilt angle of the ellipse related to the pixel edges. And instead of using a continuous Gaussian waveform, they took into consideration that when they're imaging their Fourier function, they're actually discrete. So this whole formulation comes down to here, where I'm not going to get into the detail, but after formulating this, they were able to fit their discrete form of Gaussian using nonlinear least square regression, and therefore they were able to find the centroid of this Fourier function and give you the super resolution image. However, the problem with this kind of approach is that they were computationally heavy because most of the times the single molecule localization microscope requires thousands of frames to be analyzed, and it takes hours and even overnight to give you a final image. So this is where the deep learning actually comes in. And this deep storm, which super resolution single molecule microscope by deep learning, was published in 2018, and it utilizes the UNet structure of the deep learning model. I'm not going to get into the detail. However, this UNet structure has a encoding part and a decoding part, where the encoding part actually captures the features of this image, and then it will actually output an image that we want in different form. So the loss function they utilize here is the L2 norm, where they have a predicted locations, and they also have the ground truth location. And then what they did is that they convolve the ground truth location with the pointer function that they model, and also they convolve the predicted location with the predicted location with the pointer function as well, and subtract it and square. So if the predicted location is identical to the ground truth location, and this whole term will actually go to zero, and therefore the loss will be zero. However, if there's a lot of difference, this term will actually create a large number, and therefore that can be used in back propagation in the model training. They also show that the interfraction limited image, the deep learning model was able to precisely localize each individual pointer function. And they also show that depending on the density of the emitter per micrometer square, the resolution actually varies a lot. And it turns out that when they use very, very sparse very, very sparse emitter per micrometer square, the resolution actually improves. So the blue line represents then when they use one emitters per microliter, they achieve very, very high resolution, spatial resolution. They also show that their deep storm was able to create very, very similar image, super resolution image compared to diffraction limited image. And you can also see that the original algorithm can result in a very, very crisp image. However, deep storm was not. It's still kind of blurry. They wanted to shorten the computation time. So if they used deep storm, they were able to compute one single image within 4 seconds using GPU. However, if they were to use just a regular algorithm, which is not GPU compatible, it will take about a lot of minutes. Even though the quality of the image is not as great as the conventional method, however, the time that they achieve that they were required to compute one single frame was actually a lot better than the previous one. So I think that this is a great achievement. So they have demonstrated in 2D, but they wanted to even further advance the technology by making 3D reconstruction possible. And then how they did it is that they changed the pointer function in a way that they can create a certain pattern depending on the actual direction. So in the center pointer function, in the actual direction, they actually look pretty much similar. They're kind of a circular, and then one might be brighter, one might be dimmer, but they're in a circular shape. However, what they had is that they created what they call the spatial light modulator to distort the pointer function so that depending on where the actual position, they can create different patterns that are shown on here. So depending on the pattern, they can know where the points are actually. And then you have a 2D low resolution image. They are fed into the convolutional neural network. And then from there, they can create high 3D resolution image. The model that they use is that they did not use the structure, but they use a model that looks like this, where the first part is the multi-scale context aggregation model, where they use dilated convolution to increase the receptive field while keeping a fixed number of 64 channels to extract the features and skip connection to improve gradient flow. And also after that, they use upsampling module, simple sample up module composed of 2 consecutive doubles resize convolution to increase the lateral resolution by factor of 4. And lastly, the prediction model where they further refine actual position through 3 additional convolution blocks with an increased number of channels. And the loss function they use is pretty much the same as the last time where they used the L2 norm. However, in this case, they added a second term, and this second term measures the overlap, which provides a soft approximation of the true positive rates in the predictions. So if the true positive rate is identical, then if they can predict the location that are identical to each other, then this whole terms will actually decrease, and the loss function will actually also decrease. So using that, they demonstrated that in the experimental section, this is the low resolution image. This is where they actually found the location in 3-dimensional and then applied the pointer function, and they overlaid with each other. And you can see that the experimental section and overlay section, they are identical to each other, which means that the model was able to predict with high accuracy. And using this technique, they were able to create 3D structure of a molecule that they were trying to image, which was the mitochondria. And they claimed that the resolution in lateral direction was about 40 nanometers, and the actual direction was 50 nanometer. And the computation time was 3 hours and 20 minutes. And also using this technique, they also were able to track live cells and how they move during time. And because they can exactly track where the molecules are at in Z actual direction, they can do a tracking in three-dimensional, and they were able to do this in a live cell. So overall, we learned about what diffraction limit is and why there's images are kind of blurry, and to overcome that diffraction limit, people were starting thinking about ways to do it, and then one of them was the single molecule localization microscopy, and we took a look at this one example, which was a storm, deep storm, and deep storm 3D, which utilized the deep learning model to achieve the single molecule localization microscope images. And these are the references. Thank you for listening to my lecture. Have a nice day.